We're here to talk a little about the Eden Mills Going Carbon Neutral project and the restoration of this old stable in particular, as an example of how to renovate an old house to improve its energy efficiency and along the way reduce the carbon emissions. So this is an old building that is part of the old 19th century architectural heritage of the village. The village started in the 1840s with the construction of the mill pond here behind us and the mill next door. And shortly after that, this building was built as a stable to house the horse and carriage and supplies for the general store that's on the corner just across from the mill. And it served as a stable as long as that store was in operation through the 30s, and then it went derelict in the 40s. Was used mostly as a place for the local kids to change when they were going swimming in the pond. And kids were reputed to come out from Guelph actually to go swimming in this great swimming hole, and an hour after some bunch of Guelph kids left one summer afternoon, the barn burst into flames and burnt down, just leaving the stone foundations and the ruins of the wood structure. So the family that used to run the old store on the corner decided to make a house out of it in the 1850s, and the house was just completed when it burnt. So they moved across the street and built that house there instead and lived there for 10 years and then had enough energy to tackle this mess again. And so in 1960 they built a house here that's essentially what we're in now. Unfortunately in 2002 it burnt again. There was a garage where that bedroom is now, and the tenant was refinishing an antique car and had the wood stove fired up to dry the paint while he went to bed, and in the middle of the night woke up with smoke in the house, and it took the side of the house off and the roof, and so there was a complete renovation about 7 or 8 years ago, and then I bought the house a couple of years ago as a project to show off renovation practices, and we started the whole process over again. So this house is typical of many of the old houses in Eden Mills. It's got stone foundation, built on rock, because this is Niagara escarpment country here, and houses are generally raised slightly above a crawl space that has exposed rock, and some of them have lower levels, like this one does, that walk out full story, but the floors are built right on the bare rock. And framed upper story and construction methods of 3 or 4 decades ago for the framing. And no specific measures to make them particularly airtight in those days. That didn't concern people. So to improve the energy efficiency of houses like this, the first thing that has to be done is to improve the insulation and airtightness of that envelope. Everything from floors to walls to windows to roof and ceiling. And only after that do you worry about the mechanical equipment inside. So the eco-energy plan, eco-energy program that was a federal and provincial shared program to encourage homeowners to upgrade their buildings, had a very systematic approach to how to evaluate the upgrades, and it gave a shopping list kind of incentive program for rewards to do specific tasks around the house. And the challenge here was to try to do something in every category. Something in every category of the envelope, something in all of the mechanical systems, and in the lighting and water efficiency. So the most important task we had here was to tighten up this leaky old envelope. The first thing the energy auditor does when he comes in is he puts a blower door test in the front door, cranks it up to try to depressurize the house to 50 or 75 pascals and see how much air volume that is, and then express it in terms of the air volumes of air change per hour. And this was a very leaky house when he tested it. It was about 8.5 air changes per hour under those test conditions. That's with the fan running. So that's not how much wind would be blowing through the house on a normal day, but it might be 1/10 of that. And it's, you know, a very good objective test of how leaky the envelope is, and it also helps you find out where the leaks were. So he has his fan running, and then you walk around the house and you feel with your hand or a smoke pencil to see where the air is leaking. And in this house, it was all around the basement walls, coming through the stone. It was where the framed house was sitting on top of the foundation wall, because this house has cantilevered floors that extend out over the foundation wall, make this bigger. And you often see it in the living room bay window is cantilevered out over the foundation wall. And that cantilever space is rarely sealed airtight, so it's a big leakage path. There was air pouring down all of these pot lights in the ceiling, because they're just holes through the ceiling, and then the attic is ventilated, and it's a great place for air to run through. Normally in the winter, those would be chimneys, and air would be blowing up through the pot lights, and the blower door test air just shoots out of them, because they're just a hole through the ceiling, as is wherever the wiring goes up through partition walls, where the plumbing stack goes up through an outside wall or the plumbing wall, and the plumbers never seal those, and the electrician never seals those. So those are all leaks that go from someplace inside the wall up into the attic, which is ventilated to the outside. The air sealing process here involved spraying the inside of the foundation wall with a couple of inches of spray polyurethane insulation. We had to gut much of the basement to do the renovations of partitions and to make rooms out of spaces that weren't rooms before. And so while the stone walls were open, we had a urethane insulation contractor come in to spray the spray urethane on. And although it's thought as an insulation, it's really as good as an air barrier, continuous airtight barrier. And any windows that we had open, we sealed around the window framing, and we sprayed into all of the headers where the second floor, this main floor, sits on top of the foundation. Especially those cantilever spaces, we filled them with foam. And we filled behind the electrical panel where the electrician had punched several holes to get wires in from outside to inside, and where the Bell telephone guy had punched his hole to bring the phone cables in, and so on. Lots and lots of holes. So it takes lots and lots of time and attention to seal them up. And the Eco-Energy report, the energy auditor's report, said that we could probably reduce that air leakage of 8.5 air changes per hour down to something like 7, based on the experience of thousands of renovations in Canada. And when he came back to do the post-renovation test, actually we had cut it in half. We were down at about 4.5 air changes per hour. So the energy auditor was delighted, said it was the best result he'd seen in an old house like that. So it shows that it is possible. Still not as tight as what a modern house would be, but pretty good. Part of the other work on the envelope was insulating the stone foundation. So we excavated around the outside of the house, and we can show you pictures of what it looked like before. And we attached a couple of inches of rigid insulation board around the whole exterior. We dug down to the foundations, upgraded the foundation drainage while we were at it, and insulated on the outside of the stone, and then we covered off with a cement stucco board for the finish as the weather barrier. And that served two purposes. It insulated the house, the foundation, better, and it also put the big mass of stone more inside the insulated envelope of the house. So that stone now is warm, and foundations like to be kept warm if possible. And it also helps even out temperature fluctuations in the house during the day and night when the weather changes outside, and having those many tons of stone inside the house helps even out the conditions. We also finished off the basement with some framing and insulation and drywall. And we used an insulation that's made locally here in Milton out of recycled slag from the steel mills. So that's a mineral fiber insulation. And we insulated the floor as well, because the people that lived here before said it was just horrible standing on that floor, either in the winter when it was stone cold, literally, or in the winter when it was cool and clammy and wet because it was in direct contact with the bedrock below. So we put down 1.5 inches of rigid foam insulation over top of that, and attached some plastic heating tubing, and then covered the whole works with a poured floor of gypsum, another 1.5 inches of gypsum, and then finished it with engineered hardwood floor. So now we have a floor that's insulated and also has the heating tubing in it to make it a little warmer than it would be. But the most important improvement there was the insulation. So one of the favorite places for air to escape from a house is up a big chimney through a fireplace. And in fact, when fires are on, they even increase the amount of air that's being sucked out of the house. And they may suck so much air out of the house that there's a net energy deficit when you have the fire on, that the house is losing more energy than the fireplace is providing into the house. So that's a conventional old Canadian fireplace. It doesn't really help heat a house very much. But the new airtight high-efficiency inserts, wood stove inserts, are very good. They do provide lots of heat into the space. They are installed first with a liner that goes down the old clay tile lined chimney, and an airtight firebox is inserted into the old fireplace opening. In this case, the old fireplace liner was cut out of the way to make clearance for the new insert. And the insert is essentially a wood stove, an airtight wood stove. And the new ones are rated to US Environmental Protection Agency, EPA ratings for particulate emissions. And to be sold in Canada, they should have an EPA rating on them that says they produce less than a certain amount of micrograms of particulate per hour with the fuel charge. And so wood heating is a form of renewable energy in houses that is appropriate in some parts of the country. Maybe not in cities, maybe not down in valley locations like Whitehorse, where air tends to sit and pool in the low parts of the city. But a location like this, where firewood comes floating down the river every spring on the spring flood and is delivered to your back door, essentially, it's good. And wood is renewable fuel. A number of people in the village have pellet stoves and pellet furnaces, which get their fuel from the forest industry waste of sawdust and bark and so on. So ideally, a wood stove or wood burner can help the house ride out power failure. We frequently have interruptions in power here, probably once every year or two, and they often happen in the winter. So our fanciest heating system doesn't work so well without power, so either you need to back it up with a generator or have a wood stove that gives you a little heat. So the way we installed this one is we cut out the old liner for the old fireplace, and we pulled a chimney liner down the chimney and found the smallest of the wood stove inserts that would fit here, because we like small stoves that burn hot. And this one is a small Regency manufacturer that the local wood stove store in Rockwood, Wellington Wood Stoves, supplied to the project. And it was installed in probably 3 hours, so it's not a major project. And then it has a little fan incorporated with it, which helps distribute the heat from over the firebox into the space. So pot lights in a ceiling that connects to an attic are a bad idea, and we were going to change all of these out and replace them with surface-mounted light fixtures, but instead we decided to seal up the backside of the pot light. We built small boxes out of drywall that fit over the pot light, still maintain the necessary clearance around the pot light, and swept aside the insulation up in the attic and sealed those boxes over top the pot light, sealed them to the ceiling drywall, and then moved the insulation back around them. And so when the house was tested again with the blower door test, we went around and confirmed that we had been successful in sealing the pot lights. They don't leak air anymore. So that's a possible renovation strategy instead of having to replace them. And it was interesting to note the pot lights that we did pull out as part of the renovation had the sticker on that these were the high quality airtight model of pot light. Some of the lamps I changed to a compact fluorescent, reflector type compact fluorescent, and dimmable as well. So the eco-energy audit also predicted how much electricity could be saved by changing the incandescent fixtures in the house to compact fluorescent. And now there's pretty well a complete range of compact fluorescent bulbs that you can relamp existing fixtures with. So some of the pot lights have those compact fluorescent dimmable lamps in them. Another interesting feature of this house is the waterless composting toilet. We had a great incentive to go this way in the water use technology because the house is on a holding tank, a sewage holding tank. The lot is too small and is too close to the river for a conventional septic tank. So all of the sanitary wastewater for the house goes into a couple of 2,000-gallon holding tanks. And when they're full, can't flush the toilets anymore and have to call the sewage hauler in, and he pumps them out and takes the septage down to Hamilton, to wastewater treatment plant. So if we used water as much as the ordinary Canadian does at 250 litres a person a day or so, then that would fill the tanks up about every month, and you'd be into a very big bill. So like most people in Eden Mills, we're very water conserving, but we had a very strong incentive to do even better here, since about 1/3 of the water use in a house in Canada is for flushing toilets. That's obviously the place to start. So the new high efficiency toilets at 4.5 litres a flush are a big improvement over the code standard 6 litre a flush, which is a big improvement over the previous 12 litre and 22 litre flush toilets, but better to use none at all. So the technology of composting toilets has come a long way in the last couple of decades, to the point where they're now, we use them commonly in remote buildings for wilderness eco-lodges and other buildings that are not on sewers or where we're trying to economize in the size of the on-site wastewater treatment system. So this toilet is a Clevis Multrum. That's a design developed in Sweden and now manufactured in Canada and the US. And it's a waterless toilet that relies on a central composting chamber with an automatic moistening and dewatering system in it. And after a year or two, it produces a benign, virtually odorless composted material. It's also ventilated 24/7 by a dedicated ventilation system. So that acts as the exhaust system in the whole washroom, in fact, as well as just the composting toilet itself. So that keeps odors out of the area of the toilet and also keeps the compost mass aerobic for the good composting action. We're here by the floor heating manifold that connects to tubing in the floor. We wanted to insulate this slab-on-grade floor, which is very cold in the winter and damp in the summertime. So after we had insulated it and were planning how to finish the floor, we thought we might as well put floor heating tubing in it while we had the floor under construction. So there's a 1/2-inch plastic PEX tubing laid on top of 1.5 inches of rigid foam insulation sheeting, and that's embedded in 1.5 inches of gypsum overpour flooring, leveling layer, and then covered with the engineered hardwood floor. So there are 4 circuits here: bedroom, hall, bathroom, vestibule. And we don't really need this for the heating because the house is heated with the air source heat pump. But maybe in 10 years there'll be some renewable source of electricity, or maybe we'll get another circuit off the heat pump that we can heat. Right now we have a small electric water heater that provides the hot water for the floor heating. And it's controlled both by the temperature of the slab and can control on the air temperature, but we'll just control it on the slab temperature to maintain like 22, 24 degrees, so minimal. The main benefit is though is from the insulation under the floor. We can talk about the heat pump now. This house is heated by an air source heat pump. It used to be heated by an oil furnace, forced air furnace, like many of the houses in rural Canada. And oil is a non-renewable petroleum resource, big carbon impact. We're looking for alternatives. So this is new technology for heating, new for Canada. It's Japanese, made by Mitsubishi, and they developed it about 10 years ago. It's still in the process of development, but this is one of the first installations around here. It takes heat out of the outside air and transfers the heat into the little air handling unit. And what's different about this system is it can continue to heat down into the -20s. So last winter, our first winter in this building, it provided all the heat for the house in all weather. And like many high-efficiency heating devices, it's got ECM motors now, variable speed direct current motors, which allow you to run the compressor for the heat pump at a variable speed. So the compressor only operates according to what the heating or the cooling load is. Also, like heat pumps, it is an air conditioner in the summertime, so we can use it for dehumidification. And the blower fan is a variable speed fan as well. So when it's on, it's very quiet. It just runs at the speed needed. And if you were aware, we've been in this house for an hour and a half today, and the furnace hasn't come on at all. The air handler hasn't come on at all because the building is so well sealed and insulated that just the heat of us being here and the lights has met the heat load of the house. When I came in this morning, this was cycling on at low speed every half an hour or so. So yeah, it's a very interesting new technology in home heating, and a couple of other neighbors in the village have since installed them in their houses. The operating cost of this will be less than half of the operating cost of the oil furnace. And a neighbor who replaced an oil furnace last year, he's still collecting data and doesn't want to be quoted for the actual numbers, but he was given a quote of over $9,000 to replace his defective oil furnace. And instead he had one of these installed, and it was a little bit more than that, not a whole lot more. And he thinks he will have his investment back in a couple of winters, two years, compared to replacing the oil furnace. We don't have the data yet, but the estimate would be $2,000 a winter for oil for a house like this, and considerably under $1,000 a winter for the heat pump. So they're operating, COP is a coefficient of performance is around 2.7 on days like this. So it's giving you about 2.5, 2.7 times the amount of heat as the electricity energy that it consumes. And even at minus 30, it's still operating at a positive COP, still at maybe 1.5, still giving you 1.5 times as much energy as it uses. That's the essence of a heat pump. Use a small amount of energy to move a larger amount of energy. We're standing in the old oil furnace room of the old stable. So there was an oil tank and a forced air oil-fired furnace in here before. So we removed all of that and changed this room into a bedroom. Part of the old oil furnace room into a bedroom. The other part is the mechanical room with the heat pump and the water heater in it. And we cut a piece of the wall out here, 2 days of whacking away at the old fieldstone wall. You can see from the depth of the windowsill and the reveal that it was a deep stone wall. And we finished this wall. This is part of the area that has the sprayed urethane insulation on the inside of the stone walls, and then we framed up and insulated with the mineral fiber bad insulation and drywall. And then on the outside, this is where we insulated with the 2-inch SM extruded polystyrene insulation and covered with the cement stucco board. And regular good quality residential windows. It's low E argon double. Insulating spacers, vinyl frames, so nothing nuts, but good state-of-the-art residential windows. And as equally important to the quality of the window is the quality of the installation. And so the installer was certified as an installer with good installation practices, which we feel is really important. So the windows got set into a square plumb rough opening with the frame sealed airtight to our air barrier system of the wall. And so we're confident that the whole assembly will be airtight. So it's one thing for the window to be airtight, but you want the installation to be air and weather tight as well.